Okay, guys, now that we have a pretty decent understanding of work and how to calculate work values for various forces, I want to get back to what the point of learning about work is, and that is that work is related to this broader concept of energy in some really important ways. And so we're going to see here that what work is all about, as you can see in the title of this video, is all about energy transfer. It's about transferring energy from one object to another object, or alternatively from one form to another form. Now, I mentioned in the very first video that we're in this unit, we're thinking about specifically when we talk about energy, we're thinking about mechanical energy. So I just want to remind you about that for this unit, we're thinking about just what we call mechanical energy, which, remember, is the energy associated with moving objects. So the energy associated with moving masses. And there are two different types of mechanical energy that we noted. We noted kinetic energy, which is the energy an object has if it's actually moving, and then this other type of energy, which is called potential energy, which is the energy an object has if it has the potential to start moving. And I want to hold off on potential energy. We're going to be focused in this video here. We're going to be focused on kinetic energy, the relationship between work and kinetic energy. And this is something that's called the work energy theorem. So that's what we're working up to, what's known as the work energy theorem. And potential energy, we're going to come back to next unit. We will mention, or we will talk about potential energy, how to calculate potential energy values and their relationship to work, but that'll be next unit. For now, I want to think about how work can cause a transfer of kinetic energy from one object to another. So that's the big picture. Let's kind of get into the nitty-gritty of how we're going to think about this. So let's imagine just a kind of a simple situation. Maybe I've got the ground here. And maybe for now we'll imagine it's frictionless, this surface, this ground. And I've got some object, whatever, I'll just make it like a box or a crate is on the ground, big box or crate. And I come in here and I stand here and I push on it. And by pushing on it, of course, we now know, since there is no friction, the box is going to move. And since the box moves, I'm going to end up doing work on the box. And what's the result of that work going to be? Well, the box is going to start to move. So I might say here, all right, I apply a force here, F applied, and maybe I apply it over some small distance here. So I apply it over some small distance here. So let's imagine, actually, maybe we could even give some numbers if we wanted to. Let's say that the applied force here is, make life easy, 10 newtons, and I apply that over a distance of 2 meters. So I push it to the right over a distance of 2 meters to the right, and maybe I'll tell you that the mass of the box is 5 kilograms. So this is the situation, and again, there's no friction, so there's no other force doing work. Gravity doesn't do work because it's perpendicular. Normal force does no work. So the total work done, the work total, is just equal to 10 times 2 meters, 10 newtons times 2 meters, which gives me 20 joules of work. So that's the work done. And what I'd said to you now, or I said to you earlier, I mentioned that this work has also got to be equal to, this has to be equal to energy. Somehow this is the energy, this means 20 joules of energy is transferred. That's the meaning of saying that I did 20 joules of work. That means I transferred 20 joules of energy from me to the box or crate, whatever it is. So I did work, right? I mean, this took energy from me. Not a lot. I mean, 10 newtons isn't a big force, 2 meters isn't a great distance. So I might not feel so tired after doing this amount of work. But if I pushed it a lot harder, if I pushed it with a force of, say, 500 newtons over a distance of like 50 meters, I'd be really, really tired at the end of that because I'd be using all of this energy. And when I say using the energy, what I'm saying again is that the energy is transferred from me. I'm doing the work, my muscles are doing work, I'm burning calories, I'm creating energy, transferring that energy from me, in this case, to the box. And so what we'd like to do is see if we could figure out, well, all right, if there are 20 joules of energy now in the box, how is that energy manifested in the box? Like what happens to the box as a result of gaining energy? So maybe I'll write that down. So the question here is, what happens to the box when it gains this energy? And it's no great mystery. The answer is it starts to move. It gains velocity. It gains, or actually I'm going to say it gains speed. It gains speed. Okay. So let's, to kind of break down the math on this a little bit, I want to go back to something we'd learned previously about, which is Newton's second law. So I'm actually going to take a little bit of it's going to seem like a tangent at first, but you'll see it isn't really a tangent. So maybe I'll do it over to the side here. And I'm going to remember Newton's second law. I'm going to remember that F net equals ma. I'm going to remember something else. I'm going to recall the fourth equation of the kinematic equations, the big four. I'm going to say V final squared equals V initial squared plus 2 times A times the distance. We used to call the distance delta x. Here I'm just going to call it d. And what I'm going to do is now I'm going to rearrange this a little bit. I'm going to rearrange this equation here. I'm going to take this equation and rearrange it. I'm going to say this, if I subtracted the initial squared from both sides, I would get this. So just so we're clear here, I just subtracted the initial squared from both sides. So on the left-hand side, I have v final squared minus v initial squared equals 2ad. And then I can go ahead and divide both sides by 2 and d to get a all alone. So if I divide both sides by 2d, I would get that a equals v final squared minus v initial squared over 2 times d. And now what I'm going to do is I'm going to take this thing, which is another name for a in the kinematic equations, and I'm going to plug, since it's another name for a, I'm going to plug it in for a up here. And when I do that, what I'm going to get now, if I continue here, if I can go back to Newton's second law, I'm going to say F net equals m times a, where a is v final squared minus v initial squared divided by 2 times d. And I'm going to just kind of rewrite this slightly. The first thing I'm going to do is I've got a 2 in the denominator, and I'm going to write that slightly differently. I'm just going to pull 1/2 out front. The same, dividing by 2 is the same thing as multiplying by 1/2, right? So I could write this as F net equals 1/2 m times v final squared minus v initial squared all over d. And then the next thing I'm going to do is multiply both sides by d, and I get F net times d equals 1/2 m times v final squared minus v initial squared. And then maybe I'll do one more thing, which is I'm actually now going to go ahead and distribute the 1/2 m. I'm going to distribute it to both terms in the parentheses here, and that's going to give me a final equation, which maybe now I'll actually write over here. I'm going to put it here so we can refer to it. What is this going to turn into? It's going to turn into F net times d equals, right, that was this side of the equation, equals 1/2, now I'm going to distribute the 1/2 m, that's going to turn into 1/2 m v final squared minus, distribute it to the second term, 1/2 m v initial squared. And we now have an equation, which we've derived, and if you didn't follow every step of that derivation, it's not really not the end of the world. Hopefully you did, but we end up with this equation, which has a name. This is known as the work-energy theorem. So to understand why it's the work-energy theorem, if we take a look at the left-hand side, F times D, we know that that's work. This is work. Work right there, F times D. And since it's the net force, what I'm going to say here is it's the total work. It's the total work done by all of the forces. And then the right-hand side is this thing, it's 1/2 mv final squared minus 1/2 mv initial squared. And it turns out that this thing, 1/2 mv squared, is kinetic energy. So if we go back up, we mentioned earlier that there are two types of energy, and one of them is kinetic energy. Kinetic energy, abbreviated K, I'm going to tell you now, is equal to 1/2 mv squared. And it is measured like energy and work, it's measured in joules. 1/2 mv squared. So what I have here is this equation where this says the work total equals the final kinetic energy minus the initial kinetic energy. And whenever we have final minus initial, I'll just remember that what that means is change in kinetic energy. So this is an alternative kind of shortcut way of writing the work-energy theorem. These are both two different ways of writing the work-energy theorem. I could say it's F net times D equals 1/2 mv final squared minus 1/2 mv initial squared, or alternatively, I could say the total work done is equal to the change in the kinetic energy. Okay, so to see how that applies to our problem up here, we noted that the total work done, that's going to be the left-hand side of our equation, we said the total work done is 20 joules. So in my work-energy theorem now, if I go to the work-energy theorem, the total work, that's this side of the equation, is 20 joules. So now I'm going to go ahead and say work total. Maybe I'll do this in a different color so we don't get too confused. Let's do it in green. Work total equals the change in kinetic energy. We said the work total earlier is 20 joules, so that's going to be equal to 1/2 the mass of the block, which is 5, times V final squared minus 1/2 5 times V initial squared. And I think I said in the problem, I said let's assume V initial is 0. The block starts from rest, so we'll do that substitution. That means that if this is 0, then this whole term is 0. And I get 20 equals 1/2 of 5 is 2.5 V squared. And then that leads to, if I divide both sides by 2.5, I get 8 equals V final squared. So V final is the square root of 8, which is, I don't know, what is that, like 2.8-ish meters per second. So that's how we can use the work-energy theorem. Now I just want to point out, some of you might be thinking, well, we already know about F net equals ma, and we already know about the big force, so why do I need the work-energy theorem? And the short answer of it is that you don't necessarily need this tool, in the sense that in theory you could always use F equals ma and kinematic equations, but as I think you'll see, the work-energy theorem makes solving certain types of problems much, much easier. And it is alternatively, I think, a helpful way of thinking about problems in terms of forces producing energy transfers.